It's important to recognise gravitation as a special case of circular motion, especially when we're talking about things like satellites or moons or planets or really anything that orbits anything else. It's just a special case of circular motion, and everything we know about circular motion still applies here. So we know that the net force of an object in circular motion is equal to mv squared on r. I'm using a capital R here, but it doesn't really matter. And so, of course, net force always acts towards the centre of the circular motion. And so in that case, this is gravity. We know that acceleration always equals v squared on r, and we know that v is 2 pi r on t, where t is the period and it's measured in seconds. Sometimes a satellite might be what we call a geostationary satellite, and a geostationary satellite has a period equal to 24 hours for Earth. So it stays stationary relative to the Earth. It's always over a particular location on the Earth. Combining what we know about circular motion and universal gravitation, we come up with a whole range of different expressions and ways of calculating different values for satellites in orbit. So net force we know is equal to mv squared on r. By Newton's second law we know it's equal to mass times acceleration, and by universal gravitation we know it's something only influenced by gravity. Net force will be gmm on r squared. We can combine all those with some other quantities and get another expression for net force being 4 pi squared r m on t squared, where t is the period and that's the mass of the smaller object. Acceleration also v squared on r, or 4 pi squared r on t squared, or gm, big M, on r squared. We can combine those again into a useful expression called Kepler's law. Kepler's law is this one here. It's worth knowing. It states that the radius of orbit cubed divided by the period squared is equal to gm on 4 pi squared. What's important to note here is that this part of Kepler's law is constant. So if you're talking about satellites orbiting Earth, g is going to be constant, m is the mass of the Earth, so it's going to be constant. 4 pi squared is of course constant. And so what that means is this part of the equation here is constant for bodies orbiting the same object. So for satellites in orbit around the same object. So for planets around the Sun, this is constant. For moons around the same planet, this is constant, and so on. We'll see what that means in the next slide. Here we have two objects in orbit around a larger object. They could be planets around a sun or moons around a planet. They're basically satellites in orbit. So we have a red one that is at a radius r and has a period tr, and the purple one, which is at a different radius p for purple, and has a period p. What Kepler's law tells us is that the radius of the red body cubed divided by its period squared will be equal to the radius of the purple body cubed divided by the period of the purple body squared. So often you'll be told, given three of these quantities and asked to calculate a fourth, and you will do it with this form of Kepler's law here. This could even be the same body at two different points in time. Maybe it's a satellite that's in low orbit, is moved out to further out to a larger orbit. How does its period change? You can solve that by Kepler's law as well. So if any two bodies in orbit around the same body, Kepler's law holds. The radius cubed over period squared will be equal. It's a very useful formula.